So one of my viewers mentioned in a comment that I really ought to put more diagrams and pictures and stuff in my videos when I'm explaining these things, just because I think it would make it a little bit more easier for you guys to understand. And that is a valid point. I should probably do something like that. I don't have anything prepared for this, so I think I'm just gonna flash some of my pencil sketches for the schematics for this guy on the screen, and I'll highlight any areas of importance as I go along. But yeah, so Stackish Interpreter. I almost said Skittlebits. Stackish Interpreter, Part 2, Vlog number 2. So since the last vlog, some changes have been made to the hardware, naturally. It seems to be a recurring theme amongst these vlogs. Not much, but as you can see by the schematics, there's a few more features, and that's because there are a few things that I overlooked with the last, prototype of the architecture. But that's why we make prototypes, because we're bound to miss a few things here and there. In fact, in this prototype, I even missed a few things, so this is probably going to have to be rebuilt again, but that's okay. That's what these prototypes are for. Yeah, so some changes. We now have this funky circuit back here. This is something that I completely neglected in the last revision there, or the last prototype. And this is basically the loops counter. So I mentioned in the last video how some of the instructions actually have a loops option, which basically means I can take the same instruction and run it up to 15 times. And this circuit is what's going to take care of that. So basically, the way it works is this register is actually the lower portion of the opcode. So the op register is actually split into two parts. So there's this part down here, and then there's this part up here. And there will actually be a third part that will actually take these two bits here, and that will actually dictate flag selection from these, but I obviously don't have that circuit yet, and we're going to discuss that later on, but for now, we're just talking about this. Yeah, so this is the op lower part, where the actual loop information is stored, and then above that is just a basic resettable counter, and that's clocked by the control ROM, of course, and both of those go into a digital comparator, which is basically just a consecutive line of exclusive OR gates all tied together at the output, and this torch is on when the loops are completed, air quotes. Basically means if these two are equal. So, not really sure how to explain it any further than that, other than like if you were to loop something 3 times, or if you want to loop something 3 times, a 3 would be loaded in here, and as the state machine started running its loops, this would be incremented one by one, and at the third iteration, this register will be loaded with 3. It'll be compared with that register, which is loaded with 3. It'll be equal, and this line will turn on, signaling to the state machine that it is done. Some other changes, small one, there is a 0 flag for the register, or not the register, I'm sorry, the address out. So anytime that the address going to the memory is equal to 0, this will be set, and we can of course save this information in this single bit register here, and that information is also sent to the state machine. I'm going to be getting to the state machine, don't you worry, but I want to cover the architectural changes real quick. Other than that, there really isn't much, except for there is another adder. So there used to be, with the address circuit, there used to be only one adder. There is now 2, and the reason for that is the instruction move immediate actually has the option to move up to 15 pieces of information onto the stack. Well, obviously that means the opcode or the instruction in memory can be up to 16 bytes long. So in order to accommodate that, when we're skipping instructions, we need to take the length of the instruction into consideration when we're skipping. So the reason why we have that second adder is when we're skipping and it happens to be that the next instruction is a load string, it will take the information found in the, if I can get to it, in the loops register here, as well as the program counter and such, and it'll add it all together. So that's why the second adder is necessary. And it sounded like I only listed 2 operands. So you'd think I'd only need one adder, but truth be told, uh, it's not just that we're taking care of. We're also doing the whole increment decrement thing. So that's why we need two. Yeah. And then lastly is just an upgrade to the adders. I can't remember who said it. I'll put it in post. Just that person who said it gets credit. But somebody said I should use, what's his name? Boy, I'm just forgetting names left and right. I'm sorry. The name will come to me. Cube something. Benny's Cube. Yeah. Somebody suggested that I use Benny's Cube instant carry adder. So I decided to do that. I've been reserving, using these things just because they're not the easiest thing to turn into a full-fledged ALU, but I think I can get away with it here because all I'm doing is just using an adder. So that just saves time in processing. We don't have to wait for a carry to propagate. Hell, we could probably make this 16 bits wide if we really wanted to. Probably not necessary. I'm probably not going to do it. And I think as far as the architecture is concerned, that's pretty much all that's changed. The next thing, of course, is the ROMs. This looks a little bit more complicated. And by complicated, I mean bigger. So in the last version over here, what I basically did was I took all of the microcodes that I was going to possibly use and put them in one big table. Well, here's the thing, is these microcodes, they encode basically three pieces of information. One is the source and destination for data. The second is address modes. So if we're moving to memory or from memory, it'll encode the addressing mode. So if we're addressing based on program counter, stack pointer, or substack pointer, or if we are incrementing or decrementing, or if it's before the decrement or after the decrement, or before the increment or after the increment. So there's all that information. Then there's other information such as like resetting flags or clocking flags, or just moving this thing, which is just a multiplexer. Yeah. So there's each one of these lines will have that information kind of encoded, but ultimately it's independent. So what I mean by that is, if I have like move to the A register based on the program counter, and I have move to the B register based on the program counter, that's basically two instructions. Now, what I could do instead is I could have a move memory to A and move memory to B, which is two instructions, and then I could have address based on program counter, which is another instruction. So what that ends up with is three instructions. Now, you might think that 3 is greater than 2. That's not an advantage. But when you're working with, quite a number of combinations, it actually becomes a little bit more advantageous. So instead of having to list out every possible combination of address modes and move operations, I basically just have two tables that I reference, or in this case, 3, because there's also that control information I mentioned. And it is a little bit bigger. Actually, is it? Yeah, it is bigger. It's only bigger by like 3 lines though. So that one is like 24 lines long. This one is 16. No, it's only bigger by 2 because this is 15, this is 8, and that's 3. So it's only bigger by like 2 lines. So it's not that big of a loss. But of course, these tables are huge, and that's just because of poor foresight on my end. So the wires were not optimized to have all these. So what I mean by that is basically the address control lines are like here and over there, and some of the move operation lines are here, and there, and some of the miscellaneous control lines are like all over. So it's all over the place. It's all jumbled. So I think in the next revision, what I'm probably going to do is I'm going to bundle the wires a little bit more appropriately, so that address control lines are over here, move control lines are over here, and miscellaneous control lines are over here, and then each one just gets their own tiny little ROM. So that should help shrinkify things a little bit. Yeah, and of course, because we're controlling 3 tables, it requires a total of I think it was 7 or 8 control lines. So the number of control lines from the state machine is a little bit larger, but it also means I don't have to have another decoder to actually take the state information and translate it into control information. So that just saves on time from traveling from the state machine, or information traveling from the state machine to the controls. So just small stuff like that, little improvements. On the subject of the state machine, this little guy, this guy's been giving me hell, man. Like, this thing basically went through 3 revisions before I finally got it to where it is. And I think it's complete, but knock on wood, right? So hopefully this should be the last revision, and I'm pretty happy with it. It's, fairly sizable, but I think if I fold this on itself, it should at least make it a little shorter, if not a little taller, So this obviously isn't going to be its final form. It's going to go through some revisions and such, but yeah. So facts about the state machine. It is a total of 32 states. In fact, I actually have the diagram, because I said I was going to do that. Yeah. So there's a total of 32 states, but a lot of these instructions are kind of sharing state paths. So if I had given each instruction its own state path, there would have essentially been about 48 states total, which in something like this, it really isn't a big deal to add more states, because honestly, adding more states is just the equivalent of adding another line here. So adding another state is not that big of a deal. What is a big deal, though, is adding more transitions, because currently, and this is just, intrinsic with circuits that act as state machines, one transition equates to one line in the decoder. Oh, I forgot to mention, this is basically just a decoder. I mean, this is literally a decoder with some of the outputs going through register back into some of its inputs. And I'll go into how that works a little bit here in a sec, but this is literally just a decoder, and states are represented by like a handful of the inputs and outputs, and transitions are represented by the lines. So one line equates to one transition, and this decoder basically has 63 lines or 63 transitions stored in it. Now, again, adding another state, that isn't an issue, because you literally can just add another line. That's not going to expand it too much. It's not that big of a deal. But adding more transitions is a problem, because that means you have a bigger decoder. And I didn't completely do the math on this, but if I had given each instruction state branch its own path, basically, the number of transitions would have easily exceeded 64, and that's not including some of the branch transitions that are necessary. So with this, sharing all of the paths like I got it set up the way it is, means that we have 63 transitions, which means this is basically the smallest this state machine is going to get. So you're probably looking at the diagram and this, and you're probably wondering just what the hell is going on. Basically, this thing is, as I mentioned in the previous video, is dictating the execution operation of these ROMs. So similar to how a traditional Minecraft computer works, you have the ROMs, which encode control information, and then you have the program counter, which kind of goes through them sequentially. This basically takes the place of the program counter, but it doesn't move sequentially. It actually moves in just about any order I want it to. So, let's see. So basically, each instruction can be described as a series of micro instructions, and those micro instructions can be represented by states. And those states are stored in this decoder, and the state machine, when clocked, will actually run through the states in that particular sequence to execute that instruction. It's a little bit, complicated and cumbersome, but I'll go into more detail here in a sec. But as far as instructions are concerned, like I said, this should be the completed and finalized design. So all 16 instructions are stored in here. However, I've only tested 13. And that's not out of laziness. That's just because I physically can't test something that's not there. Yeah. So the jump instruction or the skip line instruction or whatever it is, that requires the flag information in order to work. You could argue that I could just, sit here and manually change the flag status on the input here. Too lazy. Rather have the computer do it for me. And then the other two instructions I haven't tested are in and out, but that's just because I don't have I/O to test with, which again I could have just built it super quick but I wanted to get the video out ASAP. So yeah. So out of the 16 instructions, oh yeah, last video I said there were 17 instructions. Now there's 16. I basically combined the compare and the skip instruction because, in all honesty, those are pretty much always used together. So there's no point in making them two separate instructions. So I just made them one. So now there's 16 instructions, and all 16 instructions are in here, but I've only tested 13 of them. Yeah. And then I suppose you're probably dying to know just how exactly the state machine works on both, a more detailed level and on the grand scheme of things here. And I will do my damnedest to try and explain that if I can, hopefully, because this isn't complicated, but if you go into detail, it can be, but nonetheless, I'll try. So basically, the premise of the state machine is it's basically like a logical map. If you're looking at the diagram, you can see these kind of paths that kind of flow around the piece of paper there, kind of these arrows that are moving from one circle to the next. Those are basically your logical paths. So depending on what information we give this state machine, will determine what path the state machine actually takes. And so basically the way this works is it's basically just memory. So up above we have the decoder, down below we have the encoder. And so this decoder will basically select one of these 63 lines. The encoder will then activate one of the 63 lines and encode information. So right now it's in state 0, as shown by these 5 pistons here. And if you actually look up in the top left of the diagram, there is state 0 up there. So based on that, you can see there's 2 paths that state 0 can go to. It can either go to itself, or it can go to state 1, and that's dictated by the reset line over here. But we're actually not going to concern ourselves with that just yet. What we're going to do is I'm going to try and explain to you how this works. So imagine it's in 0. What would happen is the 0 from the register would feed into the state machine. Never mind all of this. Pretend that isn't there. So 0 would come in, and line 0 on this decoder-encoder combo here would be activated. Well, once it's activated, whatever is on line 0 will be presented. So let's say like 23 was presented. So when 23 is presented, it'll go to the input of the register, and when the register is clocked, 23 will be stored in the register, and 23 will be fed back into the state machine. So effectively what we did was we jumped from state 0 to state 23, and that line represented the transition from 0 to 23. And then same thing, let's say we're at 23, and it goes all the way through and it activates line 23. I don't know exactly where that is. I think it's like right here. 5, 10, 15, 20, 21, 22. Yeah, it's right here. So let's say it activates 23, and at 23 we have like a 5. Well, that 5 is going to propagate all the way through and get to the register, and then once we clock the register, the 5 is going to be stored, and we've effectively jumped from state 23 to state 5, and that 23rd, transition line that 23rd line represented the transition from state 23 to 5, and you're probably noticing a pattern that the line is going to represent the state that it's currently in, and it's going to hold the next state. You're basically right, but a lot of the times it doesn't line up one-to-one like that, because a lot of the times you'll get branches, which you even saw in the first state there. 0 actually has a choice between going from 0 to 0 or from 0 to 1, and that can actually take up 2 lines because they're 2 separate transitions. So basically each one of these lines will have an encoded piece of information that represents the state that it's currently in, and it'll hold the information of which state it needs to go to next, is basically what it boils down to. And then the way that branches work is basically what you have is, we'll do the 0 thing again, right? So let's say both these lines, they represent 0. Well, when it's in state 0, both these lines should be active. And that's not good. You don't want that, because then you're getting 2 next states being fed into the register, and that's going to conflict with stuff. It's going to cause stuff to break. You don't want that to happen. So the way you do that is you actually have input lines that you use to differentiate between other lines. So let's say both these, like I said, represent state 0, and one holds 23 and the other holds like 18, right? You could have one of these inputs, say like, we'll say the reset, because it's already programmed like that, right? So you could have the reset kind of dictate between which one will be active based on the status of that. So you could say that this line would be active if reset is a 1, and this line is active when reset is a 0. So as a result, once the state gets to 0, it will either go to 23 or 18 depending on the status of that reset bit. Now, once it goes to either state 23 or 18, it may not need that reset bit anymore because those states might look at other information to determine branches, or they might not branch at all. They might just proceed to the next state. But nonetheless, lines can choose to ignore inputs entirely. So with a standard combinational or sequential decoder, what you would have to do is you'd have to go to every line that looked at, that I'm doing a poor job of explaining this. I'm sorry. So basically, there would be 2 lines that you would have to look at, sort of. Yeah, you know what? Let's just forget that because that's too difficult to explain. Basically, instead of a traditional sequential decoder where every combination is listed out, what it basically is lines have the option to completely and totally ignore a line. So, for example, you can see right here, this line for quite some time is actually just completely ignored. It isn't until it gets all the way down here that it's even considered. So when a line is ignored, it's basically just the line is skipping over it. It doesn't interact with it at all. But even so, even when you have all these lines being ignored at various points and stuff, at no point should 2 lines ever turn on at the same time. Even though it's kind of a funky decoder, it still acts as a decoder in that you always get a 1 of n output. So that's the basics of a state machine. And then, of course, how this state machine works, we're going to have to basically run through some of these instructions and kind of walk you through what happens when they're executed. So let's do that. So first things first, the initial state of the state machine is 0, and that's not determined by anything. Basically, what it is every single line looks at the reset bit and is basically looking for this reset bit to be off. So if it's on, none of these lines are basically going to output. And that's exactly what we want because as a result, there will basically be 0 on the output here, which will set the state to 0 and effectively reset the state machine. So simply by turning on the reset input and clocking it a few times, the reset state is initiated and the state machine is now ready to start executing instructions. So as you can see, the reset state is currently, or the state machine is currently in the reset state or state 0, and the control outputs is basically relaying set information. So basically all of these ROMs, they all have an extra state where they basically do nothing. So for the most part, the address information that's doing nothing, the where is it? Having difficulty finding it. Well, that's weird. Where'd it go? Oh, my bad. The functions are basically doing nothing. The only thing that's doing anything is the move information, which is currently in state, or in move 1 scenario, which if we actually go through here, I don't know why that's shifted over like that, is basically this one right here, which is a reset. So when it's in the reset state, it's going to send reset information to the move information, and all this does is basically write to every single register with no source. So it's basically guaranteeing that it will write a 0 to all the registers, which if we look, It actually already did that. So, yeah. And then, of course, you may have noticed, real quick, I just want to go into this detail here. You may have noticed this funky circuit. So, if you watch the computer tutorial series, you'll know that sometimes you need scenarios where information needs to pulse, because a lot of this stuff requires a falling edge at some point. So this is basically my pulsing circuit, and that's tied to the clock input. So when it clocks, it's first going to send a signal to all of these, which will turn off the torch, and so any blocks that are sitting above it will get depowered, and these lines will basically turn off. And remember, a 0 on these lines is basically a no operation, so it's not going to affect anything. And then after a few ticks, the register is pulsed and the new information is stored. And then once that's done, the torches are turned back on and the information is then presented. So if the same information is basically presented, but we need to run it again, this will basically ensure that the torches will pulse so that we at least get a falling edge at some point. Yeah, just small information such as that. But anyway, according to the diagram and according to reality here, once it's in the reset state and the reset bit is turned off, the next state that it will go to is state 1, which we can actually see on the output bus. So you can see that the next state is already present. It's going to go into state 1, which means once we clock it, the register is going to store 1. But it's also sending out the next control information. So here you can see we're going to move into function 1. We're going to move into address op 1, and we're going to move into move operation 2. So all that information is already stored. And I actually have some spreadsheets. I'll pop those up. So all of that stuff is encoded. So when I say it's going to be, function 1, address op 1, move op 2, that basically means that it's going to perform something with these. I can't remember off the top of my head what it is, but the spreadsheet will tell you what exactly that means. And it basically, since this is state 1 that it's going to go into, that's an op fetch state. It's basically going to involve something with reading memory based on the program counter. So if I go ahead and clock it again, we'll actually see that information loaded. Just like that. That would be my phone. And we are now in state 1. Now, since it's in an op fetch state, it's going to try and fetch the instructions from the instruction memory over here based on the program counter. So because the program counter is initiated with 0, thanks to the reset state, it's going to select the first instruction in the program memory, which I have gone ahead and thrown in the push random number instruction. So the push random number is 0001, which is what we got, but then that particular instruction also has a loop option. So we have the option to loop or to push up to 15 random numbers onto the stack. We're going to go ahead and push 2. So that information is currently being distributed throughout the computer, and that is all going to be saved in the various registers respectively. So the 2 is going to be stored in the loops register down here, if I can move. So we can already see that 2 is ready to go in there. And then the op code information is ready to go into this register. We can already see that it is backwards, but that 0001 is in fact there. Now, you may have noticed something interesting, and that is I've got this mux here. So you might be wondering, or maybe not, why I have that here, but I'm going to explain it to you anyway. So basically, the reason why I have that mux there is that mux allows me to choose between what's about to go into the register or what's currently in the register. And the reason why I do that is because the state 1 is an op fetch, but it's also an op decode state. So it's currently, while it's fetching the instruction, deciding which logical path in the state machine it's going to take based on that instruction. So I could have gotten away with, not needing that mux, because in all honesty, what I could have done is I could have used state 1 to fetch the instruction and then moved into state 2, where then I chose which path to go. But I figured I may as well just save a state and mux it. It's really not that big of a deal, and frankly, I find it a little bit sleeker. So Actually, you know what? It is kind of a big deal because one instruction cycle, or sorry, one clock cycle to fetch an instruction versus two clock cycles to fetch an instruction is kind of a big deal, and it does kind of accumulate over time. So any clock cycles that we can save, you know, it's good to me. So this basically just allows for the information to be presented early so that the state machine can get a head start with determining what path to go down. But as soon as it clocks, the mux is going to switch with what's already in the register, and the state machine is going to continue operating off of that. And just to show you that I'm not pulling this information out of my ass, I haven't clocked this yet, but according to the diagram, if the instruction is 0001, it's going to go from state 1 to state 20. And as you can see, we are currently in state 1. The next presented state is 10100, which is 20 in binary. So if I go ahead and clock this, what's going to happen is it's going to move into state 20, of course, and state 20 is going to tell the decode ROMs to read the random number generator over here and then write to memory based on the stack pointer. And of course, it's going to adjust the stack pointer based on the decode information, or not the decode, the address information. So it's going to, I believe, increment. But yeah. So this is again where we need the pulse, because if you may have noticed, we now have a choice. We can either proceed to Q1, which is basically just going back to state 1, or we can loop to state 20 over and over and over again, which is actually what we're going to do, because that particular choice is determined by the loops complete or loops done input, which as you can see is currently off, which makes sense because that register is currently stored with 0, or excuse me, 1, and that is stored with 2, so it's not done. So it needs to continue on looping. But of course, we don't have an alternating state, like we're not going from 20 to 21 and back to 20. We're just going from 20 to 20 over and over again, so we need a falling edge. So that's why we have the pulse circuit there. Yeah, so currently we are, like I said, in state 20, which pushes a random number, which is already generated. Not a very exciting random number, but it's a random number nonetheless. And that's going to be pushed into the stack, which is right at the beginning of memory here. So if I go ahead and clock it again, we'll actually see, because it happens on the falling edge, that stupidly boring random number is going to be pushed onto the stack, like so. Just like that. And of course, because our loops aren't complete, we are still in state 20 if we actually go over here. Still in state 20, but our next state is state 1, and that's because the loops done or loops complete line is currently on, because the loop track counter register has been incremented, and now the two registers are equal. But we're still in state 20, so it's still going to push another random number, which is perfect because we wanted it to push two random numbers onto the stack. So if we go back to memory, let's actually see what that number is. Oh, another super fantastically boring number. And these are all high bits, so that's not going to make the next part fun. But it's going to push that number onto the stack. And because it is a stack, naturally, it's not going to go to this one. It's going to go to this address over here. So if we go ahead and clock that, we'll see that, once again, stupidly boring number being pushed onto the stack, like so. So now that the state machine is in state 1 again, of course, it's going to be doing another opcode fetch based on the program counter, which was incremented from the last time, which means we're going to be fetching the next instruction here, which is 1100. And that particular instruction is a add instruction, which actually takes the top two pieces of information on the top of the stack, pops them off, and adds them together and pushes them back onto the stack. I'm doing this instruction because this is probably one of the longer instructions that I've got in this instruction set, clocking at a whopping 6 clock cycles. So we'll get to see that kind of happen in action. So at this point, it is currently fetching that information, and once again, it is muxing before the register, because the register is still storing the last instruction, but we kind of need that information now. So it's muxing the new information, and the decoder is currently figuring out which state it needs to go to next, which just so happens to be 2. So if we go ahead and clock that, we're going to move into state 2. Now, one thing I mentioned is that a lot of these instructions actually share branches or paths or whatever you want to call it. And this is a good example of both a long instruction and one of those instructions that share paths with other instructions. Because if you notice, the transition from state 1 to 2 only considers one bit, and that is the op3 bit. And the reason why is because I worked out the instructions so that it worked out this way, but any instruction that starts with a 1 is actually needing state 2 to proceed state 1. And then, of course, from state 2, it has to split off again, but not too many, different splits, of course. We're going to be going from 2 to 5 since this is a 1100 instruction, but even then, the transition from 2 to 5 is only looking at these two bits here. So even if, it was a 1111, it would still go from 2 to 5 because those instructions all share the same path up until state 5, at which point it splits off to 7 and 8, and then, from there goes to 8 to 9, and then 9 splits from 9 to 13, 14, and 15. It's a lot of different paths, but basically I combined a lot of the paths where I could just to kind of save on transitions. So that's the reason for that. Oh, but yeah, so what is state 2 doing? State 2 is basically popping information off of the stack. So remember, we loaded the stack with those two very, very boring numbers. Well, what state 2 is going to do is it's going to start popping numbers off of the stack and loading them into the A register, or rather, it's going to pop a number off the stack. So this last number here is going to be moving into the A register, and if we actually fly over here, we have the information present on the bus. If we go down to the registers, we can see that the A register write is primed to write. It hasn't written yet, but it will as soon as we clock it. And then, of course, the state machine is going to move to state 5, and the A register is now loaded with the number that was present in memory. Now, in state 5, we're actually taking the information that was popped off of the stack and stored in the temp A register, and then we're going to push it onto the popped stack. Now, I believe I explained in the last video that there is a popped stack, which is basically a stack that stores everything that's popped off the main stack. But again, the rule with this computer or this language is anything that is popped from the main stack must be pushed onto the pop stack, and the unpop instruction can then unpop anything that's been popped. It's a little confusing, but I hope to go into detail about it a little further. But state 5 basically takes the information that we just popped from the main stack and stored in the A register and takes that and puts it back into the popped stack. So we'll go ahead and clock that. And we can see that information being stored at the foot of the popped stack. And then, of course, in one fell swoop, we went from state 5 to state 8. So the reason why we went from 5 to 8 instead of 5 to 7 is because if you look at the transition from 5 to 7, that one actually requires a 1 across the board. So this needed to be a 1111 instead of a 1100. Versus the transition from 5 to 8, which actually requires these two bits to be 11, and then either this bit or this bit must be a 0. Since this is a 1100, it meets both those requirements, and it goes from state 5 to state 8. Now, one thing I want to mention is we have that OR statement there. State machines like these, especially ones that are based off of combinational decoders like this, they don't do OR statements like that very well. So anytime you see an OR there, understand that that's actually two lines. So there's one line that looks at the opcode and checks to see if it's a 110, and then there's another line that checks the opcode and checks to see if it's a 11, skip the middle bit, and the last bit's a 0. So basically this met the criteria for one of those bits. Actually, I think it probably met the criteria for both. So both of them were probably active, breaking the one rule that I said you really shouldn't break, but whatever. It didn't matter. They were both pointing to the same location. So it went from state 5 to state 8. Now, state 8 basically does the same thing as state 2. We're popping from the stack again, so instead of taking this number back here, we're going to be taking this lovely boring number right here, and we're going to be moving it to the B register. In fact, if we look, we have that stupidly boring number there, and the B register is primed to clock. or to write, I should say. So if I go ahead and stand here, clock the state machine, we will see that number clocked into the register. Now, from state 8, we go to state 9, which is a non-conditional transition. It has to go from 8 to 9. And in state 9, we're basically doing the same thing as in state 5, where we're taking the information from the B register and pushing it onto the popped stack because it was a popped item. So if we actually go back to the popped portion of memory right here, we will see that number once again pushed onto the popped stack like so. Now, once again, we have a branch. Of course, this one is looking at 3 possibilities. We have the branch from 9 to 13, from 9 to 14, and from 9 to 15. We're taking the transition from 9 to 13 because that one specifically looks for this sequence on the input. The others, of course, looks for 0, 1, and 1, 0, respectively. And of course, as you can see, we are currently in state 13, which this is the final state in this sequence of states for this instruction. And this one actually takes both the pieces of information that we currently have stored in the A and B register and adds them together. So if we actually look, we have the added information up at the top. And this is why I kind of wanted more interesting numbers, because honestly, you can't really tell much has been done to this damn number. So you'll just have to trust me when I say it's been added. But basically, it's going to take that number and it's going to push it back onto the stack. Well, since the stack pointer is currently pointing at 0, it's basically just going to push it back to the foot of the stack. So if we go ahead and clock this, you'll see that new, stupidly boring number pushed onto the bottom of the stack. Or rather the top, but it's pointing at the foot. You get the idea. And then, of course, because it's done, it's going to go into the op fetch state again to fetch the next instruction, which we don't have, so there's really no point in it going into that state. But nonetheless, it's just doing what I programmed it to do. So it went from state 13 to state 1, and now it's ready to fetch the next instruction. So yeah, that's pretty much everything. Obviously, there's a lot more to the state machine, as you can see, but it's fairly straightforward once you know the basic concept of a state machine and, of course, state diagrams. So you could probably just, study that yourself and figure out what exactly is going on. Or maybe I can go into further detail in another video. But for now, I think this video has gone on long enough. So that is the progress update for the Stackish interpreter. So I hope you enjoyed. If you did, like, subscribe. It's all really appreciated. Not really necessary, but it'd be great if you did. And I will be seeing you guys in the next vlog update when hopefully we will have this entire circuit completely finished and hopefully cleaned up a little bit because, frankly, I hate rat's nests. This is just annoying. But yeah, we'll save that for the next video. Hopefully it'll come out a little bit sooner than like 3 months. So, bye.